Alhamdulillah, bismillah wa salatu wa salam ala Rasulullah. We are all welcome to the class this morning. So we are going to continue, as we can see, with our topic of looking into machine learning applications, taking clue from the past successful utilization while exploring the present and future possibilities. So following the announcement of few of assignments, so we've gotten a couple of responses, so which we are going to be discussing hopefully later on. Today we're going to look into basically, so we've gone through some of the application possibilities. Shortly before we move into trying to show us a couple of example of what I call proof of concepts. At least some of those applications we are discussing, they are not things that are out of reach or that we cannot do. So each of these applications are something that are really practical, so doable, and they are very much applicable, and some of them can actually be turned to startups, so depending on area of application that's been targeted. So before we move to the proof, we're going to show ourselves a couple of proof of concepts, so by way of real-life publications, while some of them are other patent idea applications. So, but before then, we are going to look at, in all of these particular applications, like I said, something that are unique. So we want to look at some of the algorithms that are often utilized from our own research team and people we've worked with or we've collaborated with. So among the very common one that's often used, like I always say that it's always good to keep it simple. So we have the KNN, the K-nearest neighbor. We have discussed it before. If you look at our archive videos, you can see there, what is KNN, how does it work? Then we have decision tree, we have neighbors. So these are among the first point of calls, algorithms that we quickly look at when we have new problems to be solved. So of course, we also have the artificial neural network. This is chosen because of KNN, K-nearest neighbor is chosen for its simplicity. Also decision tree. So very simple and easy to explain to your client. Sometimes you have clients that are interested in how the model works. In that case, it's very easier to use decision tree because it's a day-to-day, it's an algorithm that is often used in day-to-day activities, even in normal engineering, business. Every day, we have things that look like decision tree. Whenever you want to do some things, the easiest way for you to plan is to have a tree. Okay, I'm here. What can I do? Should I go for this business? No, I want to go for maybe, okay, let's say 2-year term. We have a long-term business or we have a short term. Then you break it down again. Then you break down again. So everybody are very comfortable with something like this. That is why decision tree is always a first point of call, especially for application that has to do with businesses or with where the client are interested in following up with how the actual model work, or where the interpretation of the application matters, because this is also another very important thing to take note. If the application involves interpretation, especially in business, you want to really know which of the attributes, which of the features are actually contributing to this particular output. So in that case, decision tree could be a very good algorithm to start with. However, there are situations whereby the system is just interested in predicting an estimated value that can be used in real time to be able to prevent disaster. Like you want to know when a particular compound will reach the explosive temperature, because you don't want it to reach that explosive temperature. So in that case, no one is really interested in how that prediction is taking place, but we are more interested in the accuracy of such prediction. Because we don't want a system that will predict that the estimated explosive temperature is 23. Meanwhile, it is supposed to be 21, which means disaster will happen before we actually detect it. So depending on the application, we get to select which of these algorithms work for us at the appropriate time. And of course, also at the forefront of them is the artificial neural network, especially if your data set is sizable yeah, you can go for artificial neural network because it needs a little bit sizable number of data set to work or to get reasonable results. We also have what we call the extreme learning machine, which is a variant of one of the variants of artificial neural network. So, but it has only one single layer. So, because as you know, neural network, you have to tune several parameters, how many number of layers you want. Do I need 5 layers or 10 layers or 17 layers, layer 1, layer 2, layer 3. Once training takes place here, it goes to layer 2, it goes to layer 3 until the end of the layers. Even in each layer, you have to determine how many neurons. See, okay, in layer 1, I want 10 neurons. In layer 2, I want 14 neurons. In layer 3, I want 15 neurons. So how do you know the number of neurons in each layer? Which means you have to tune the parameters. So it takes a lot of time to be able to come up with the best neural network topology that you are going to use for your system. So because of this time factor, then people came up with different kind of options. Among the variants is the extreme learning machine, which is just single layer. And it has proven with the single layer neural network, that was a theorem often proven that with a single layer neural network, you can actually you need to focus on tuning the number of neurons in that layer. How many neurons am I going to have in that particular layer? Based on that, you can be able to get the best possible result. And we've often used this particular variant of neural network in several of our works, often with very excellent results, actually. Often with very, very excellent results. Now, so we've often used this extreme learning machine as a means of bypassing the challenges of neural network when it comes to the several parameters that need to be tuned and the time, it's very time consuming to be able to determine those parameters. But with extreme learning machine, you only focus on just the only hidden layer it has, only one layer. So then you are going to be working on the number of neurons in that layer, which become very easier to do. And often, especially in classification work, it's something I recommend a lot. So you always performing really excellently well in classification. Also in regression, we probably use it also for several successful applications. Then we also have the sensitivity-based linear learning method, which is a variant of neural network also. So incorporating sensitivity analysis at one of the layers of the system. So also we have the support vector machine, which I identify as most commonly used. And I'm going to tell us why do we use it most often? Because one of the unique reasons why we use support vector machine often, here we say support vector machine and SVR. This one means support vector regression, because originally support vector machine was developed for classification only, you see, but was later extended to cover regression. So that is why the regression aspect of it is called support vector regression. However, sometimes people just call it support vector machine to refer to either regression or classification, which is also fine. And it's one of the machine learning algorithm that after this series we are on, we're going to try to bring it up to look at it in detail. What are the unique capabilities of support vector machine that has made it so much important and appealing to in several applications. Now, one of the very big reasons, a very important reason is that support vector machine does not suffer from what we call cost of dimensionality. Cost of dimensionality is it has a system that made it to be able to easily escape getting stuck in the local minima, or what we call the cost of dimensionality problem generally. And what is cost of dimensionality? That is when you have large number of features. You have several features. Remember when we talk about feature selection, I explained the term cost of dimensionality, where I told you that if you have, let's say, only one variable x1, then you are expected to have at least maybe a minimum of 10 raised to the power 1 samples to get reasonable result. When your features become X1, X2, X1 and X2, it means you have two features. You are expected to have something approximately 10 raised to the power 2 samples, which is 100. And when your feature become X1, X2, and X3, that is 3, you are expected to have like 10 raised to the power 3 samples, which is like 1,000. This kind of growth is known as exponential growth. That is the number of samples needed to achieve similar results or a kind of acceptable result is exponentially growing with the number of features. So you can see, when you have one feature, you need 10. When you have two features, you need 100. When you have 3 features, you need 1,000. So when it becomes 4, X1 to X4, you have 4 features, you're expecting like 10 raised to the power 4. So, and in reality, the number of samples are fixed. Your client will send you data. When you ask them, oh, do we have more data? And they say, no, this is the only thing we have. I give an example. One of the very popular permeability work we used to work on, this permeability data has like a 376, around 376 data points. And then inside it, we're having 15 features. 15 features. Ordinarily, we are supposed to have like 10 raised to the power 15 samples. Do the mathematics. That is the number of samples we are supposed to have. But here, we are stuck with the number of samples, 376. We cannot get any extra, and we have 15 features. What can we do? So hardly will you see any machine learning algorithm that will work in this kind of situation. We have to work on what we call feature selection. Try to reduce the number of features. Study these 15. Use different feature selection algorithm or methods and try to track it down. I mean, reduce it down to maybe to like 5, 6, 7, and sometimes then you can have algorithm that can work with it. But with 15 features and 376 samples, I can bet it with you, you can only get any system that will work for you in any of the system. However, we found out that support vector machine has a very wide and unique capability that even when you have this kind of extremely high number of features compared to the number of samples that is lacking, so it's still able to perform. So that is why I said this is most commonly used by our team, because especially when you have material science applications where the data set is very few. Sometimes we have like 8 features, just 16 samples. Imagine 8 features, 16 samples, 8 features, 25 samples. Extremely few number of samples. Support vector machine still able to get something because it has a special capability for being able to work on data set that has high dimension. That is, when the number of features are really high, support vector machine will still do something for you. Another unique area, personally, from my own personal experience, is when the data is really few, support vector machine will still be able to get something reasonable for you. For my experience so far, no other method ever worked for us in this kind of situation. When you have like only just 16 samples, 25 samples, you train, they hardly work. But support vector machine has this unique capability. So that is why we have to try to keep track of it. When your data is really small and you are struggling to get good results from KNN, from decision tree or any other method, remember to use support vector machine. So this has been working really for us. And then you can see in some of the proof of concept that we're going to display later on. Next is we had what we call the type 1 and type 2 fuzzy logic systems. It's an area that later we hope we are going to have the opportunity to also discuss fuzzy logic. What is fuzzy logic? And then how does it really come into machine learning, and to what extent is it important? See, can we really improve the machine learning accuracy by incorporating fuzzy logic system? So like we talked about type 1 and type 2, we used to work with type 1, but later we also found out that type 1 fuzzy logic is a little bit restrictive. Then we moved to type 2 fuzzy logic system. So it's one of the topics we are going to discuss later in details, and see how and what it has brought to the, or what can it bring to the table when it comes to machine learning modeling. So it has really also worked a lot. So we did a lot of work using type 1 and type 2 fuzzy logic system. Then after that, we moved to hybrid machine learning techniques and also the ensemble, because sometimes these are just, I can see it is, etc. here. So there are so many other methods, but these are very common ones that we do call upon to use for the system. Like I told us before, there's no machine learning algorithm that will always achieve the best in all situations. But some of these have really distinguished themselves, especially the support vector machine. But yet, we are not saying it's going to work for you in all situations. In fact, sometimes if your data is really much, it might come down in terms of performance compared to other methods. Yeah, because one of these challenges when the data is big, it has a lot of optimization and quadratic programming problem that you have to solve. So it takes a lot of time during the training. However, once the training is done, then the testing set becomes very easier. So like we're going to pick support vector machine later on, and we're going to discuss it in more detail. How does it work? And why is it really unique that even when the data set is very, very few, it still has that capability to achieve something reasonable where other methods might fail. Now, so when we work on individual, sometimes also we might need to have a look at hybrids, that is, try to mix them together, the output in hybrid and ensemble. I'll explain briefly the difference between the two of them. You see, in hybrid, you start working with one method, and then once the output of this method is ready, then you feed that output to the next one. So in that case, but with the latest technology of using what we call stacking ensemble is more or less working like an hybrid, directly or indirectly. That is why the thin layer between hybrid and ensemble is getting thinner and thinner every day. So before it used to be totally two different things, whereby you have in hybrid, an output from one is coming, and that output is going to be used to train another model. See, but an ensemble is you train many methods, many algorithms, and then you try to let them vote for you to select which one is going to be the final answer. However, with the coming on board of the special type of ensemble, which we call stacking ensemble, that is changing the story, because now in stacking, we can actually also train several models. Instead of just making them vote, no, we take their output and use that output as a new feature to be used in training another model that's going to take the final decision. That's why I said with the inroad of stacking into ensemble, then the thin layer between hybrid and ensemble is becoming thinner and thinner. Now, so we do use hybrid system and also the ensemble system, as we are going to see, a unique, we can see here. Now, because like I said, we say a further shift in paradigms. So the reason is that I used to say, let the data speak. It's a policy and it's work. However, we are saying so that data may speak more clearly. So the idea of ensemble and hybrid method that you might have to go for it when the individual models fail, or you don't start with it, you try the simple ones. So what if they fail, then you might not have option but to go for hybrid or ensemble, in which case we want the data to speak even more clearly. So it's depending on the kind of underlying information that is within the data, because the idea is what's called data mining. When you have your data, like the mining engineer we do, looking for what they call it, gold and diamond and so many other material that are very pricey. So machine learning try to do what we call the data mining, try to mine the data to see what is the information inside it. So sometimes an individual model might not be able to provide all the needed information that are hidden from this data. They cannot detect it. Or sometimes when you train your model, they were able to detect something fine. But if there's a little change in the data that is coming in the testing set, especially when you want to deploy it into production, that is, you want to use the prediction in real life. So sometimes you cannot guarantee that the data that will come in new is going to be the same exactly like the one you use for the training. This is where the idea of hybrid and ensemble can really assist us, because with an hybrid or an ensemble, they have a kind of more information within them. Imagine you build a model 1, you have another model 2 on the same data set. Another model up to model N, your N can be any number you like. It could be 150, it could be 180, it could be 250, depending on the time you have. So if a new sample is now coming with this huge number of models, at least majority of them should be able to understand the pattern of this new sample that is coming in. So this is an advantage in this particular sense. And that's why I said, so that data may speak more clearly. That if we really want data to really speak more clearly, because we want the data to speak to us, we want to be able to understand the underlying principle that this data, the underlying information that this data is carrying all about. That we, as human beings, when we look at it, we cannot see them, but the system we are developing has that capability. So with an hybrid or ensemble system, hopefully you can be able to do different combinations. This one and this one, they are combining them together. Others on here, we allow them to go straight to meet another second combination. That could be different level of cascaded combinations. You see? So until you finally get the final result that you hope that is going to be better, especially in real life environment where you don't know the kind of data that might come next, this could be an advantage since it has a lot of information. So like we used to say, permit me to use Agbajo laughing soya, we say it. So when you are many, I mean, you have the capability to actually solve problem in a better way. So this is a reality. Sometimes we have to go into this particular mode, especially when the data is getting really challenging, or we want, sometimes when you run individual model, it could get to a place that the accuracy gets stuck. Imagine you are solving a problem for your client and the accuracy gets stuck at just 92%. And your client is requesting for us to accept this data, this model from you, at least we need minimum 97 to 98. But now you have tried all your individual models. The maximum was 92. What do? So you have to go for hybrid so that the data may speak more clearly. Okay, let's go for hybrid. And often than not, I've demonstrated for us several times that ensemble can actually push you to even get 100% easily, depending on how you are able to carefully deploy them. So we have discussed several application areas, and we have actually discussed different types of ensembles and how they work and how we can take advantage of them. We can refer to some of our archive videos for revisions on those. Now, another we'd like to mention is some of the optimization techniques. You see, sometimes because in machine learning, it is very important to have hyperparameter optimization. Hyperparameter. And I've differentiated between what is parameter and hyperparameter. Hyperparameter, they are those parameters that they have direct impact on that particular machine learning algorithm you are using. For example, k nearest neighbor. There's k there, the number of k. How many k neighbors am I going to use for the training sets, for the training system? So we need to determine the number of parameters, what the value of k. That is an hyperparameter tuning. So we have also a neural network, how many layers you are looking for. If you are using extreme learning machine, okay, how many hidden neurons are you going to use for that single layer? So each algorithm with its own different hyperparameters. So we need to have ways to optimize. Parameter optimization is very, very important. Because if, for example, you have k, you just develop k, the default value is k is equal to 1. You find out that you got like 85% accuracy, and then class, you submit, you finish, this is my result. That is not fair to that algorithm, because the same data, I decide to come back, I decide to check the parameter, I use k is equal to 3, k is equal to 5. I found out that with k is equal to 11, I was able to get 99% accuracy. Can you imagine from 85 to 99%? This is because parameter can make a big difference in the performance of machine learning model. So we don't underrate it. So because of this how important the parameter optimization is, we come up with there are several algorithms to do the optimization. But for our own experience, now our team, some of the methods we have been using, I like the very simple systematic hyperparameter optimization. The simple one, which is the one I described for us in several of our encounter earlier, whereby it's more of you based on knowledge. For example, for K nearest neighbor, we have K, and we have also the distance measure. So I start with K because it's very, very important. So I search for my base K, use K is equal to 1, run the experiment, K is equal to 3, K is equal to 5, K is equal to 7. If you are dealing with binary classification, until you get the best value of K. Once you get the best value of K, then you fix it. Maybe if K is equal to 11, then you start looking for the best quality measure, which could be Euclidean distance, it could be Manhattan distance, and also for other distance measure that could be used. This is an example. This is called the simple systematic hyperparameter optimization. We pick it one by one. For example, if I'm dealing with support vector machine, I know that the most important hyperparameter in support vector machine is the kernel function. So I go for like maybe polynomial or Gaussian or any other. First, once I find out the best kernel for that particular data, then I move to the next level, which is C. You see, the regularization factor C, which is very, very important. I start searching for the value of C. By trying C is go to 0.1, it's go to 0.5, 1, 2, 3, until I get the best value and I move on. This is simple systematic start. However, sometimes also, maybe due to time, you just want to explore some other better things, we use actually genetic algorithm. Genetic algorithm is another area of artificial intelligence that mimics the human genetics. So I then try to develop an algorithm that can search for best parameter from among many of them. It use the principle of genetic like a mutation and also for others. We hope we have the opportunity also to discuss some of these kind of optimization techniques in our future encounters. We also have the gravitational search algorithms. So that's we do use. We also have particle swarm optimization. So which are optimization techniques that are developed following the natural system of swarm animal that we can say they appear in swarm in the kind of a setting like the birds, like the fish, and so many other optimization algorithms that they study the natural way of animals like the bee. You look at the bee, they are so organized. You see the ant, we have what we call the ant colony optimization. There are several of these. They come under what we call the computational intelligence algorithms. We are nature inspired, or we call them also, another name for them is nature inspired computing. So whereby they study nature, they study the animals like fish, how they swarm around, how they identify their prey, and they used to develop an optimization algorithm. They study the ant, and then they start to come up with ant colony optimization and so many other kind of optimization like this. So we do also engage them when we talk about optimization techniques for our algorithms, because the hyperparameters are so much important. If we miss very important hyperparameter value, then it can actually derail the entire system we are building. Now, so that is on that. Then on this now, we now say that once we select the appropriate one, the final note that will always let us realize that what to remember, very important, is that remember about machine learning classifier is what we call no free lunch, that machine learning algorithms, they are tools, not dogmas. Some of them might be very successful in some application, but still we don't generalize that these are the best. We can always get others that might be better. And new ones are being developed every day, especially ensembles and hybrid methods are coming up every day to see that, okay, how can we make things better? But from our experience and what is going on, the next thing people are really looking up is the ensemble. Because most of the competitions out there, they always find out that no matter how much time you devote to developing a single algorithm-based model, the ensemble will always be the one to perform better. So no classifier is inherently better than any other. So we need to make assumption to be able to get good generalization. Make sure that you do the appropriate hyperparameter tuning. It's very, very important. You cannot just declare that a model is not working fine, even though you have not taken your time to do the appropriate optimization. In fact, I used to tell my student that it is not fair. You see, a student will just declare that this algorithm is getting 92. Another one is getting 96. When I probe further, they did optimization for the second algorithm. They didn't do it for this. I say, it's not fair. If you didn't optimize the parameter, the hyperparameter of an algorithm, you cannot declare that it is not working for that problem. You decided not to make it work. So, and it is not fair. You can't report that in a research work because that is going to be a kind of fraud or reporting something that is not correct, either because you don't have knowledge of it or you deliberately want to promote your own model that you like, of course, which is not correct. So also we say try simple classifier. You can see in what I told us, we used to try simple classifier, individual ones, especially support vector machine. Mashallah, is all. Most of the several applications where others fail, support vector machine work because of that capability of being able to deal with high dimensional data. When the number of features are really many and you have very few features, support vector machines still have a very unique way of getting reasonable results where others failed. So then I say here, it's better to have smart features. This is another thing I want us to pay attention to. So when you are going to start gathering data for your own application area, so as some of us have already identified where you want to work, you see, it's better to have smart features and simple classifier than simple features and smart classifier. What do we mean by this? That is, if your feature is good, if the data sample you are gathering is okay, it is better than, and then you can get a very simple classifier might do the work for you. But if you get a very bad data, and what is data? Data comes from the feature. Because when you have X1, X2, X3, and then you have the target Y. The combination of all this is what we call data. So if your feature is not correct, imagine you want to predict if a student is going to pass an exam or not. Like I'm teaching a course now, I want to predict a student who will pass or fail. I should look for features that are relevant to that particular application area. For example, what is the attendance rate of this student? How often does he come to the class? Is he always absent in the class? Yeah. Is the student always coming to the class? Or he only comes once in a while? This is a very good, to me, this is a very good feature to look into. Then what was the grade of the student in the previous course? That is a prerequisite to this course I'm teaching. However, if somebody say, okay, which kind of food is the boy fond of eating? To me, what has food has to do with a student passing my course? You see, he like eating fruit or he like eating this. How does that affect the course the student is going to pass or fail? I mean, you can put it there, but then there are some features that even you yourself, by looking at it, you know that no, this feature is not relevant. So we want features that are very relevant to what we are developing. That's what we call smart features. However, we want a point of warning that we should not over trust our judgments of features. Sometimes we look at feature and say this feature is not relevant. It might be relevant. That's why I always ask people, put as many features as possible when you are developing your model. Gather as many features as possible. Let machine learning algorithm tells you that those features are not good. Because we have feature selection methods. The system will run and be able to tell us this one are not relevant, this one are relevant. I say we should be conscious of it, that we should not over trust our own judgment, because we have seen people who are in engineering, they believe that, oh, there are 3 parameters that are better, other parameters are not good. But when we run data mining application on it, we found out that among the 3 they rejected, 2 of them were better than the 3 they were using. You see, the same thing in medical. So when we want to do a prediction, we want to get all the data for the patient. Yeah, our medical doctor has experience. Yeah, we respect them for that. However, we don't want them to restrict us on the kind of data they give us. Because sometimes they say, okay, if you want to predict for diabetes, you need to have the blood sugar, you need to have this. We say, okay, thank you very much. In addition to this, can you give us other data set, other features that you don't use? Because this is called discovery new things. And this is what machine learning want to do. There are some data set from the patient that usually doctors don't look at because based on their training, they are not relevant. But machine learning are coming to identify some of these neglected features as very, very important to determining or detecting diseases at very early stage in patient. So these are some of the things we have to pay attention to. So when we say better to have smart features and simple classifier than simple feature and smart classifier. So if the classifiers are really very nice and near to what we want to model, maybe it is better, but we should not overdo it. So, but it's better than having simple feature that are not relevant, and then you are looking for very smart classifier. So because of the principle of let the data speak, let the data speak. So it's always good to have better data. If your data is clean, data is nearer to what you are modeling, maybe you get better result. And then use increasingly powerful classifier with more training data. The bias variance trade-off, we explained this before. Use increasingly powerful classifier. That is, start with simple classifier, especially if your data is few. You have very few data, you go for neural network. It's going to be a sheer waste of time, actually, because you're going to waste a lot of time and you are not going to get good result because the data is too small for that. You go use deep learning for a few data sets, it's a waste of time. Go for k-nearest neighbor. Go for decision tree. Then go for the special guy, support vector machine, because these are known to perform even when your data set is very few. Now, and as your data set is becoming more and more, then you can keep exploring, because as data is becoming more, maybe the simple algorithm might not be able to really understand the underlying system that the data is coming up with. In that case, you might have to start going to other complicated algorithms like neural network, or you might try to talk of ensemble, so that combining them, they'll be able to understand all the internal information that these data sets are actually carrying all about. That simple model might not be able to determine that. So these are some of the very important information that we need to take note of when we are trying to select what are the application, what are the model or machine learning algorithm that we're going to use when we are going to develop any of the system that you have selected to work on. Now, so I think this is where we're going to meet it at this point in time. Now, in our, what I want you to start thinking of, for those people that have responded with their assignment, there's still time for others. That is, identify, the assignment is try to identify some of the areas in your own specialization, because I know people are from different backgrounds in this class: engineering, medical, agri, economics, political science, or human sciences. Try to come up with some of your application area. Now start digging into data set. I have shared before the data set with us, and I'm going to share it, some of the sources of data set. Don't underrate the power of data set online. Try to get data set that are relevant to your own area, and then try to start looking at it. When you look at those free data, that will guide you to be able to get your own data later on. Yeah, when we go to that next stage where you are going to try to practicalize some of these things that you've learned in relation to the area of your interest. So this is what we are going to have for the day. So I'll give room for questions. And by next week, we are going to look into what we call the proof of concepts for some of the ideas that we've discussed, that we have implemented, and then how can they assist us to be able to move further in our own individual areas that we have identified. So thank you very much. I wish us all the best.